Let's talk now about infectious diseases, and specifically, we're going to use some mathematics to address the time evolution and the life history of infectious diseases. So we want to be familiar with some terminology. Okay, so this is a good chance to do an introduction. When we refer to infectious diseases, we're referring to processes that are involving a pathogen. This pathogen is invading or is living or residing in one host. And more importantly, the word infectious here has to do with the ability and action to pass from one host to another host. So we have multiple examples of pathogens. Perhaps the ones that come to mind right away are pathogens that are bacteria or pathogens that are viruses. Viruses, for example, the Mycobacterium tuberculosis is the bacterium responsible for the disease we know as tuberculosis, and influenza virus is an example of a pathogen that is responsible for what we commonly call the flu. We know that the flu season extends from October all the way through April and May, and the so-called flu is caused by the virus called influenza virus. So the infectiousness and the ability to infect others has to do with ways in which a pathogen is passed on, and these ways are called modes of transmission. There are many different modes of transmission. Here we mentioned some examples. We were just talking about these two examples of tuberculosis and the flu. These are examples of infectious diseases that are transmitted through particles that travel through the air, okay? And therefore they have the name airborne diseases. There are other diseases that for the pathogen to be passed on from one host to another host, it is required the host have a sexual encounter, okay? So those would be the diseases typically known as sexually transmitted diseases. And there are other examples of diseases that require a middleman, if you will, an intermediary. That intermediary acts effectively as a carrier of the disease. And you have examples such as malaria and dengue fever. For these diseases, that intermediary is a mosquito. Okay, in the context of malaria or dengue, humans are infected with dengue or malaria, and they are then bitten by a mosquito, and then the mosquito carries on dengue or malaria, and it bites another human, and then that human becomes infected. So in that context, an infected human with malaria cannot transmit or cannot pass on the pathogen directly to another human. Okay? And those type of diseases are called vector-borne diseases because that carrier of disease is typically known as the vector. So a common way of referring to infectious diseases is also by referring to them as communicable diseases. They can be communicated. They can be communicated, meaning that they can be passed on, transmitted. Okay, so these are infectious diseases or communicable diseases. Here's where you would like to contrast infectious diseases to other types of diseases that do not necessarily involve passing on pathogens, such as cancer or something like that, in which the process of acquiring the disease is completely independent to these interactions. But with infectious diseases or communicable diseases, there is an important element on this process has to do with passing from one host to another host. Now, we can find historical recounts, records of perhaps some of the earliest records date back to the 300s BC, when Aristotle wrote about certain agents that were capable of disease, and he called them invisible living creatures. Later, in the 1600s, Van Leeuwenhoek was responsible for establishing the existence of microorganisms. And then in the 1800s, there were several individuals. One of them is credited, Louis Pasteur, is credited with instituting the germ theory of disease. Okay, some, and then there are much more concrete historical recordings of disease transmission. But so, what is transmission? Transmission has to do with that ability to pass on the pathogen. So here is a cartoon, a drawing of one host, and this host is not infected, and this host is hanging out with another host who is also here represented with the color blue. Both of these hosts are not infected. All of a sudden something happens, and this initial host develops, this initial host is now infected, and so the transmission is, this is an illustration. Okay, so the point I'm trying to make is that we are concerned with interactions, for example, at the level of two individuals, of two hosts, and the ability for one host to pass on. So there will be some definition, some concept of what does it mean to have a contact, and when that contact is established, then there is a channel or an opportunity for this to happen, which is now the second host becomes infected. Okay, so the notion is there is an infected host having interactions with an uninfected host, and then the pathogen find its way to jump from one host to the next host. Okay, so this is an illustration, this is a drawing about how transmission goes on. We have represented here the state of the host with a color, and we're going to be using mathematics to have some mathematical representation as to how to keep track of this process, the process of passing pathogen from one host to another host. But so in reality, let me ask you this: how do epidemics look like? Okay, so here we have these are now illustrations of potential hosts, right? These are people from all walks of life, right? These are very cheerful individuals, and one way of answering this question, these are individuals from day-to-day activities, right? And in general, when you take the bus or you take the train, or you're waiting in a bus stop, or you go to a class in an auditorium, or you go to the airport, you board a plane, you go to the gym, right? Go to a yoga class, or I don't know, any activity that involves you interacting with other humans. In general, these are the type of phases that this is what you would look. You would look at people, on every day. And so unless there are some very specific signs or specific symptoms, for people to be red flag as being infected, in general, for many infections, how do epidemics look like? Well, they look like this. You look at people around you, and you couldn't really tell who is infected and who is not infected. If they're not sneezing, or they don't look lousy or something, you couldn't really tell. And in some cases, individuals that are carrying the pathogen, sometimes they don't even know that they are hosting such pathogens, right? So in general, how do epidemics look like? Well, they may look like this, like the people we hang out and interact with every day. Now, for quantitative individuals, for mathematicians, for statisticians, individuals like you, then this is a way of visualizing epidemics. How do the epidemics look like? Well, this is an answer to that question. They may look like this. This is a snapshot. This is a way of keeping a count. Here, there is a count on prevalence. This is a data set. On the horizontal axis, we have the observations are being measured every day, once a day. And then on the vertical axis, we have measurements or counts on the number of infected individuals. These are individuals in a boarding school in the United Kingdom, and this was an outbreak of the flu. Okay, so this is one example. This data set is called prevalence data. It has to do with the number of infected. Here's another example, again on the horizontal axis. The time, you have time units, and those units are now in weeks. In the previous data set, in the previous example, the measurements were taken every day. Here, the units or the scale for the horizontal axis is in weeks. Okay, and these are observations of the prevalence. Okay, this is a data set for an epidemic in 1905 in India. Okay, so in the third example, all these examples I'm just trying to illustrate to drive home the message here that how do epidemics look like? Well, if you have ways of keeping records, ways of counting, having a head count on either the number of infected individuals or the number of new cases, then you will be able to put together data sets that, when visualized, displayed, you can create this type of figures. This is the third example. These are observations about cases of measles in New York City. And here the observations, again, on the horizontal axis, these are time units. Now these are monthly observations, right? These measurements were taken once a month. And you can see how, even though this is over a much longer time scale, right? This is easily extending over 30 years with monthly observations. You look here for this data set. This is on the period over 30 weeks. 30 weeks is less than 1 year. 1 year is 52 weeks. This here is in days, right? And it goes for about 2 weeks, right? Between 2 and 14. So this is the most 2 weeks. But you see certain patterns in these data sets, right? Even you can see how they increase, so that they have the shape of increasing up to a maximum and then decaying, right? So they increase up to a maximum and then decay. And here, in a sense, these patterns are consistent. You would have to basically take a snapshot not over 30 years, but if you look at what's happening over a shorter time window, then you see how there is a pattern of having a really low level of measurements, and then they grow up to some maximum value, and then they drop, right? But because here this data set is over a much larger time period, we can see that these patterns repeat themselves, okay? But these are examples of standard data sets you find in the literature for standard diseases, infectious diseases. Now, we go back to the question of, how do epidemics look like? These were three answers to that question. They may look like this, but part of what is involved in how do they look like, when we're turning to this question about the looks, we're really trying to brainstorm of, let's use some mathematics to quantify. Here, the key is to quantify, and then perhaps it's not just so much how they look, but how they are quantified. And in that effort, we're going to have additional tools to answer this question of how do they look, what are the looks, okay? Now, let's go back to the idea of transmission. Remember that I showed you that cartoon where there was one infected host and was paired with another host that initially was not infected, and eventually the pathogen was passed on, right? So they were first blue, and then when they became infected, they were red. Well, the transmission and the action of passing on, now I'm showing you these photos of people on a day in the life, right, of different individuals in a given community. And now I'm drawing some lines here. I am trying to illustrate that, yes, this may be how people around you look like, but the notion of how they hang out with each other, how they interact with each other, that notion is embedded, it is underlined in understanding the transmission, the way in which the pathogen will find its way to move from one host to another host has to do with these lines that I'm drawing here. These lines are representing how these individuals in this community may be connected to one another. So maybe, people here on the upper left, maybe one is the chef of the other one, and there are all individuals here that may attend meetings, maybe city council meetings or something, and some other individuals may be classmates, maybe they take a class, they attend the same university or community college or something of that sort. And so this notion of denoting relationships, interactions, representing that here with a line, this starts kind of giving you an idea of the representation between interactions among individuals. Okay, so then this leads us to the question of, okay, but when we're talking about transmission, and we know transmission here is the ability to pass the pathogen from one host to another host, then we're going to define or give a definition for something we're going to call contacts. Okay, so a pathogen, examples of pathogens, a bacterium is a pathogen, a virus is a pathogen, right? And transmission is this ability to move or pass from one host to another host. Contact is defined as an opportunity for transmission of infection to take place. Okay, so a contact may refer to a transmission opportunity, or it may refer to a pairing. Remember my cartoon where there were two hosts, right? A pairing of two individuals, such that pairing, that chance in which they get together, they attend class, they they go to the same school, or they go to that meeting, right? A pairing of two individuals with the potential of transmission. These are two things that are maybe involved in a contact. And two of the most important features of contacts are going to include the number of contacts per unit of time, and also the number of different individuals with whom these contacts happen, with whom these contacts occur. Okay, these are two of the main characteristics. So when we have this notion of contacts, going back to that illustration where we have the people we see on a regular day in our lives, and we start drawing lines between people, right? So by drawing these lines, we're trying to represent those interactions between different individuals. Well, those interactions are connections. These connections is what we are going to consider contacts, right? And you can also realize that these contacts may differ from the context of one pathogen to the context of another pathogen. If we are comparing a pathogen such as the bacterium or the virus for an airborne disease, well, in the context of airborne diseases, these pathogens are traveling through the air in small particles, right? And it's a matter of releasing these particles into the air and catching some of these particles while they are in the air or while they land on a surface, right? And so in that context, a contact is going to be an opportunity to be close enough to somebody to either sneeze, cough, or breathe from each other. But if we are comparing an airborne disease with, for example, a sexually transmitted disease, there in that context, the contact will be very specific. The contact will have to involve a sexual encounter between the two hosts, right? So the definition of contact may vary significantly from one context to another context. But importantly is, once we are in one context and we have a definition of what a contact is or what a contact may involve, then we may consider how individuals are having contacts with each other, and we can represent those individuals in a certain way. And here's one way of doing that representation. That representation is giving a visualization, or at least is a theoretical means of representing the structure of contacts, the structure in a population, but specifically the structure of contacts, which is pertinent for infectious diseases. So if you represent every individual with a circle or a dot, and if you represent potential contacts or potential transmission with a line, then you may end up with a figure that looks like this. This is, in mathematics, this would be called a graph. That is a well-known branch of mathematics dedicated to the study of these things, these graphs, and it's called graph theory. Outside of mathematics, outside of mathematics, you would probably come across with literature in which this is called network science. So this can be called a network, or it may be referred as a graph, right? And there is plenty of literature and theory about this. This is a visualization of a network or a visualization of a graph, and this, in the context of modeling infectious diseases, this has to do with the word mixing. Okay, mixing is how individuals are pairing with each other, how they mix with each other, how they are interacting with each other. And when there is a very well-defined structure of contacts, right, something that may be visualized like this. Here's another example of another structure of contacts. This is referred as heterogeneous mixing. Okay, we will go in detail about the epidemics on social networks or infectious diseases on social networks. We will do that at a later time in this class. But I just would like to mention. I would like to mention heterogeneous mixing because the other type of mixing, which is the one we will start with to write down some equations, the other type of mixing is mixing that is not heterogeneous. It's called homogeneous mixing. So this is a context in which you may think of individuals in the population, say individuals in the population are represented by some particles, and you want to kind of make an analogy between these particles and maybe some homogeneous solution. So if you assume that the particles in this population have the ability to mix very well, this mix will be so well that it will be homogeneous, right? So an example of homogeneous mixing is a solution of sugar with water. So you pour sugar into a container and then start putting water, and you start stirring that container, and pretty soon you will not be able to tell, right, where the particles of sugar are because they mix so well with the water, right? And this is a cartoon representation of that type of scenario. When we refer to homogeneous mixing, we're referring to a population in which individuals and particles in that population are not really displaying a particular pattern, Okay, so in a way, this well mix means that particles are equally likely to encounter each other because they are so well intermixed, right? But this idea of homogeneous mixing, and I'm using some words here like equally likely. Equally likely means the same chance, right? And equally likely the same chance that is connected to a word in mathematics that's uniform. Uniform from the point of view of the uniform distribution, okay? In the uniform distribution, things have equal chance or are equally likely. So homogeneous mixing typically is also known as random mixing, and is the type of random that is uniformly at random, unbiased, right? So the mathematical models that we will derive first are models that use the assumption of homogeneous mixing, okay? And then later in the course, we will develop some mathematical models for heterogeneous mixing by means of social networks. And this concludes our introduction to mathematical models of infectious diseases.